Okay, all good, I guess. Yep, it sounds that we're connected. Let me just set a timer for 15 minutes for reading the papers, and then we can start. Okay, we're still going to continue on this AIRL paper that we were going through, and this is like the second part of the video. So 15 minutes focusing on it, and hopefully you will understand what's the algorithm about and all this about it. Okay. So, as talking before, this is the reward and this is a discriminator that we had. And updating the discriminator can be viewed as updating the reward function, and updating the policy can be viewed as improving the sampling distribution used to estimate the partition function. So just as a context, updating the policy can be viewed as improving the sampling distribution used to estimate the partition function. Now, if you recall, we talked about maximum entropy IRL. Now, in maxent IRL, normally we say that the probability of a trajectory to be made by an expert is related with the e to the power of summation over the rewards of that trajectory. So it's like summation over states and actions of the reward that is coming from the states and actions, sometimes as prime. Now, the problem here is that, like, if I have a bunch of trajectories, we need a normalization factor here so that this trajectory can be seen, like this probability can be seen as an official probability. Otherwise, the more trajectories we have, the more this thing will go up and up and up, and the resulting probability would not make sense. Okay, let's say I have a trajectory that is too long. How can I say that it is actually a probability? Okay, so in order to fix this issue, we have the notion of a partition function in maxent IRL. Now, what the partition function is saying is that, like, if I want to find out what is the actual probability of this trajectory, I will make it like e to the power of this summation. However, I will divide it by a summation over all of these e's for all the trajectories, okay? So I consider every single trajectory that is possible to happen, and by summing them all together and dividing this thing over that thing, I can get what is the probability of this trajectory happening. This is called a partition function, which being denoted by z. Okay. Now, the problem here is that, like, normally, because we cannot provide all of the trajectories, because, like, as you can tell, like, finding and talking about every single trajectory is hard and probably untractable. So we use sampling methods as the way that we do in reinforcement learning. So we just sample through some trajectories, and then we try to estimate this partition function by the sampling thing. Now, in order to do that sampling, they are talking about this policy thing that can be viewed as improving the sampling distribution. So it's like you're improving the policy, and basically you are improving the ways that these trajectories can be made. So you are kind of improving the sampling method that you had. Okay. Okay. If trained to optimality, it can be shown that an optimal reward function can be extracted from the optimal discriminator as this thing that f star of t is equal to r star plus a constant, and pi recovers the optimal policy. So if we reach to the optimality here, we can say that we have the optimal policy, which would be the pi, the generator, and the f star would be actually the reward function that we are looking for. We refer to this formulation as generative adversarial network guided cost learning, which is called GAN-GCL. To discriminate it from guided cost learning, which is GCL, they have just discriminated it by calling it GAN-GCL in this specific paper. And this formulation shares similarities with GALE, but GALE doesn't place a special structure on the discriminator, so the reward cannot be recovered. Now, they are talking about this ARRL, or which is adversarial IRL. Now, the problem here is that like when you are using the full trajectories as it is proposed by GAN-GCL, so as you can see, they are using the full trajectories. We will have high variance. Similar to Monte Carlo, when you are talking about full trajectories, it's normally with very high variance. So what is a better method would be to just separate all of the state actions and just going through that things. So um, it is saying that, okay, so we could instead propose a straightforward conversion of equation 2 into a single state action case where instead of using a discriminator over all of the trajectories, we have a discriminator over states and actions. So it's like d theta of S and A would be equal to e to the power of f theta for that specific state and action, and divided by, again, the same thing, and the policy of a given S. Okay. As a trajectory-centered case, we can show that at optimality, that f star is equal to the log pi star, which is equal to the advantage function. Now, there's a notation here which comes from Szilard's thesis. In Szilard's thesis, we have the notion of a soft Q function and the soft V function. And in the soft Q and soft V, we have maybe I should show it in here, it would be a better idea. So basically in Szilard's thesis, we have the fact that the policy is equal to the e to the power of Q soft minus V soft. So you can say basically that if you take a log from both sides, you will get the fact that log of pi would be equal to the Q minus V. And as you know, Q minus V would be actually the advantage. Advantage function is basically saying how much you could have if you had chosen the best action versus what you are taking now. So it is like the difference between your value function and your Q function. So here, the log of the pi star would be equal to this A star, which they are denoting as F star. And as you remember, this F thing is basically a summation over, like it's e to the power of F, and F is equal to the summation over all of the gamma times R, which is basically the same thing as the value function. Like, yeah, the value function that you would get over all of these things. So when we are talking about F in a specific state and action, you are basically talking about what is the advantage that you get here. The advantage function of the optimal policy, we justify this as well as a proof that this algorithm solves the RL problem in the Appendix A. This change results in an efficient algorithm for imitation learning. However, it is less desirable for the purpose of reward learning. While the advantage is a valid optimal reward function, it is a heavily entangled reward. Now, what is this entangled? And later they'll talk about what is the reward ambiguity problem and what do they mean by a disentanglement. So it supervises each action based on the action of the optimal policy for the training MDP. Based on the analysis in the following section, we cannot guarantee that this reward will be robust to changes in environment dynamics. In our experiments, we demonstrate several cases where this reward simply encourages mimicking the expert policy and fails to produce desirable behavior even when changes to environments are made. Now, what is their statement? Their statement is that normally when you talk about your reward function with this specific way, your reward function is quite, like if your reward is coming from this type of F, your reward function is like entangled. Entangled with the dynamics of the environment. Meaning that if you change the dynamics of the environment, your reward will change, which is not normally the case. Like if I have, let's say, a grid world, and then in my grid world, if there is like this specific thing that is my goal. Now, if I change this grid world to something bigger, this is still my goal, and I'm still trying to reach there. So it doesn't matter if I start from here or start from here. this state is my goal. But the problem is that like if I change the dynamics, if the reward is like a recovered reward is a function of states and action, this would happen. Okay. So they are trying to fix this issue by introducing the notion of disentangled rewards. Now, next part is the reward ambiguity problem, which they talk about the reward shaping thing. So the thing is that we review the concept of reward shaping. Now, if you don't know, in reinforcement learning, there is a problem of reward shaping that says that basically, like Inge et al., they describe a class of reward transformations that preserves the optimal policy. The main theoretical result is that under the following reward transformation, which is like if you can show your reward with this transformation, the optimal policy remains unchanged for any function. So what is it saying is that if you define your reward in this specific type of way, which like we call this phi of s a shaping term. So if you have defined your reward with this specific type, your optimal policy would be unchanged for any function of phi. And yeah, so this was reserved the policy. What was the problem? The problem was that if you changed, basically like if you like the problem was that like one reward could specify so many optimal policies. That was a problem. That was when the problem of reward shaping came out. So it is like, hold on, let me maybe open this. So yeah, the problem was like, for example, if I talk about a grid world, let's say, and then I make my reward function to be +1 in here, all of these maybe would be a good policy for it. Like if I go straight to the goal, or if I avoid this thing and then go to there, and then, or maybe, I don't know, like just do a cross thing. So the problem was that there's so many policies and none of them are actually showing the optimal policy here. Now, if I can make my reward to be of term of this phi thing, gamma phi minus phi, this is basically talking about how you are removing the effect of the environment on your thing. And it's like not the environment, but you are basically having this reward shaping term. Maybe it wouldn't be a bad idea if we just dive a bit more deep into this statement so that we can understand this reward shaping term better as well. So okay, maybe just let me ask about ChatGPT. What is reward shaping? Give us some background and what's the use of it. Oops. I made a mistake. I meant to copy the stick. Sorry. Reward shaping is a technique used in reinforcement learning to make learning more efficient by modifying the reward function without changing the optimal policy. Okay, I think I'm a bit lost. Hold on. Can you use bullet points so I can concentrate? All right, let's see what is reward shaping. Reward shaping overview. The purpose is that the reward shaping modifies the reward function to guide the agent's learning without altering the optimal policy. So I'm assuming that all of the rewards that come from this specific way, so if you can define any reward with you have a specific reward, any reward that comes from this specific notation of, like, let's say this is my reward. Now, any other reward that comes from this thing that is like gamma phi minus phi would be like equivalent to R without changing the optimal policies, like they are coming from the same family. So the problem is that this helps in environments with sparse or poorly defined rewards, making learning faster and more efficient. Adds extra signals to the reward function, helping the agent explore beneficial behaviors and converge more quickly. Theoretical background. Reward transformation. Eng et al. Propose a reward transformation that preserves the optimal policy. So they talk about a reward transformation that preserves the optimal policy. They are defining this R hat, which is equal to R plus gamma phi s prime minus phi s, where this R is the original reward function, the gamma is a discount factor, and this is the potential function over states. How does it work? It adds a potential difference between the next state and the current state, which guides the agent without changing the optimal policy. The transformation doesn't change the agent's long-term preferences. It only affects the immediate reward signal. Benefits of reward shaping. What is the benefits of reward shaping? Accelerates learning, speeds up the convergence by giving the agent more immediate feedback on beneficial actions. Improve sample efficiency. The agent needs fewer interactions to learn an optimal policy. And then we have the potential function can be crafted using domain knowledge, making learning more effective in complex, unfamiliar environments. YRL methods can fail to learn robust reward functions. We have the ambiguity here. Multiple reward functions could explain the expert behavior, making it difficult for RL to learn a single robust reward function. Without constraints, IRL might learn rewards that only work well in the training environment but generalize poorly. In environments with shaped rewards, IRL might capture only part of the expert's intent. All right. Okay. So there's the notion of reward ambiguity problem. So they talk about reward shaping. Now the problem is that without prior knowledge of the dynamics, this is the only class of reward transformations that exhibits policy invariance. Because RL methods only infer rewards from demonstrations given from an optimal agent, they cannot in general disambiguate between the reward functions within this class of transformation unless the class of learnable reward functions is restricted. Now, what are they arguing? That the shaped reward functions may not be robust to changes in dynamics. They say that the shaped reward function may not be robust to the changes in dynamics by studying the policy invariance in MDPs. So they just say that this shaped reward function is not robust to changes in dynamics. It is okay, like it's obvious. How do they argue this? They say that, okay, let's say if I change my transition function so that now it is outputting some other state, it's clear that there will not be the same S prime here, so it will change the equation, which is acceptable. Disentangle link rewards from dynamics. So as their next step, they talk about disentangled rewards. Oops. A reward function is perfectly disentangled with respect to a ground truth reward. So we've got a ground truth reward and a set of dynamics. They say that this R prime is disentangled from with respect to the ground truth reward and the set of dynamics such that under all dynamics, the optimal policy is the same. So no matter what is your dynamics, the optimal policy will remain the same thing. And this is like the notion of a disentangled reward. We could also experiment, include the notion of suboptimality. Under maximum causal entropy, the following condition is equivalent to two optimal policies being equal, since Q functions and policies are equivalent representations. So under maximum causal entropy RL, we've got that Q star is equal for R prime is equal to the Q star of R minus Fs. So they say to remove this reward shaping with arbitrary reward function to classes, we say that this reward can only depend on the state, the current state. Okay, so they talk about this decomposability condition where functions over current states and next states can be isolated from their sum. So there is like a function over a state and a function over an X state. This can be satisfied, for example, by adding self-transitions at each state to an ergodic MDP. Okay, blah, 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 blah. Okay, what they talk about at the end is that if R is the ground truth reward and T a dynamics model satisfying the decomposability condition, IRL recovers a state-only reward such that it produces an optimal policy in T, then this R prime is disentangled with respect to all dynamics. If a reward function is disentangled for all dynamic functions, it must be a state only, i.e., if for all dynamics T, we have the Q star is equal to this Q plus F for all S and A. Then R prime is only a function of state. In the traditional RL setup, where we learn the reward in a single MDP, our analysis motivates learning reward functions that are solely functions of states in a real truth of the. Okay. So all good. What they mention is that they have to separate the reward to be one part only state related and one part to be state action related. And like that's their new method and how they just learn this they called disentangled rewards. Okay, let's dive a bit deep, but let me first check how much time we have. Okay, so let's say what is their statement here is that they talk about their discriminator to be of this specific form. So there's like an exponential of an f, but this f is both a function of theta and a function of phi, a function of theta and a function of phi for every state, action, and next state. So they are separating one part for phi and one part for theta. So it's like they have two different neural networks. One is called g of theta, one is called h of phi, which one part they have the case of s prime and they have the case of s. Okay, so it's like for their reward they have one term for their shapes reward, so it's like they have a shaping term called h of phi and a reward approximator which is like g theta. The additional shaping term helps mitigate the effects of unwanted shaping on our reward approximator g theta. So any shaping term that comes, they are separating it from g theta. Okay, The entire training procedure is detailed in algorithm 1. Our algorithm resembles Gale. We can now parameterize g theta as solely a function of the state. Allowing us to extract rewards that are disentangled from dynamics of the environment in which they were trained. Under this restricted case, we can show the following under deterministic environments with a state-only ground truth reward. So they have like this G star and H star, and G star is equal to R star plus a constant. H star is like the V plus a constant, where R star is the true reward. F star must recover the advantage as shown in section 4. H recovers the optimal value. So as you can see, like we have a notion of a G, we have a notion of H. H is recovering the value, and the G is recovering the reward. So it's like we have the reward and we have the difference between V of S prime minus V of S. So basically we are getting the advantage here. Okay. All right, so the whole idea is that for their discriminator, they talk about this, let me maybe write this here. Their whole new way and what are they talking about is that they talk about the specific discriminator, and for their f of x, sorry, so for their f, they have two different type of neural networks. One is related to phi and one is related to theta. There's another f here and there's a notion of pi. So I think it's exponential of f over state, action, and next state. Same here. And the pi of a given s. Let me just make sure about it. Yes. So what they talk about is that if you think about this f thing, they are separating one estimator as G and one estimator as H, where your G is technically giving you the R star and your H is giving you the V. So it's like assume two different networks, all of them are training. One is for separating the reward and one is for separating the value. That's the whole thing. And this would make their algorithm. So in their algorithm, they would just obtain the expert trajectories, T of expert, initialize the policy pi and a discriminator. So you're just initializing it. And therefore the step T, from 1 to n, you collect the trajectories by executing pi, train this D via binary logistic regression to classify expert data from samples, update the revert, and update pi with respect to R using any policy optimization method. This is the whole idea of their algorithm, and then they have their experiments. So for their experiments, they're talking that they have used both in discrete and the continuous environment, and since they are separating the effective test state from other stuff, they can handle transferable rewards. So it's like if they change the environment, their agent will still learn what's going on. Let's dive a bit deeper in the algorithm, and then we can probably let go of everything for now for this paper. Oops. Hold on. Yes. Then we can let go of the parts for this paper and we can start our next paper. Maybe I'll ask ChatGPT about it. Explain the following. algorithm in the most clear way. Use bullet points and explain any technical detail. All right, so we have adversarial inverse reinforcement learning. The input, we start with expert trajectory. So we have a bunch of trajectories that are coming from the expert, which are sequences of state action pairs from an expert. Okay, then there's, so that's it. Expert trajectories, which are samples of behavior from an expert that the agent aims to imitate. Then there's the initialization phase. For the initialization, we initialize the agent policy pi, which is basically our generator thing, which defines the actions the agent will take in each state. And then we initialize the discriminator that will learn to classify whether state action pairs come from the expert or the agent's policy. Policy, this is a decision-making function for the agent that will be updated to mimic. And as we mentioned here, so it's just explaining it. The discriminator outputs a probability score. I need a little break, so I'm just gonna pause this and stop the stream for now. And probably will end the whole thing by myself. But, yep.